everyone. Hello everyone. I'm going to discuss the solution to example 4 on relative equilibrium of liquids linear motion. So here is the problem. The rectangular tank shown is 1.2 meters wide into the screen. Determine the following: the value of A sub x such that the depth at C reduces to 0.25 meters, 0.25 meter, the value of A sub x such that the pressure at C will be 0, and if A sub x is 9 meters per second square and AY 3 meters per second square, determine the maximum pressure that can develop in the tank and the point where it is occurring. So this is the given figure. We have water here and we have an opening here, so meaning to say this is exposed to the atmosphere, 0 pressure, and the direction of AX should be positive to the right, positive upward for AY. And these are the given information: 1.8 meters, 1.2 meters wide into the board. So for the first question, the value of AX such that the depth at C reduces to 0.25. The original depth is 0.5. So if the depth at C will be reduced to 0.25, that means this surface should drop 0.25. And since the difference between 0.75 and 0.5 is also 0.25, so that means the resulting surface is crossing exactly through top left corner A. So this is the expected figure, and call this theta 1. So this is also 0.25. So therefore it crosses the point of symmetry because this is also 0.25. So that the depth at C will be 0.25 also. So this is 0.9, half of 1.8. So that's 0.25. This is also 0.25, and call that theta 1. This is also theta 1. So tangent theta 1 equals AX over G, 9.21, equals 0.25 over 0.9. So that's the equation for the first question. So equals 0.25 over 0.9. So AX can now be solved. It is equal to 2.725 meters per second square. And the value of AX such that the pressure at C will be 0. So for the pressure at C to be 0, the resulting liquid surface, water surface, should cross C so that no depth will be at C, or C will be exposed. So since that is only possible if the slope is greater than this first one, so the expected water surface should cross the top cover in the following shown. So this is the expected surface, and this is theta 2. And from the figure, let's call this distance x. So the tangent theta 2, which is AX over G, equals 0.75 over x. So tangent theta 2 equals AX over 9.21 equals 0.75 over x. Now, how to solve for x? Because no liquid is spilled, final volume of air, which is represented by this triangular wedge, equals initial volume of air. So final volume of air is 1/2 area of this triangle, 1/2 of x times 0.75 times 1.2 equals 1.8 times 0.25 times 1.2. So we can cancel 1.2. So instead of volume, we can use area instead. So x is equal to 1.2 meters. Solving for AX into this equation, so AX over 9.81 equals 0.75 over 1.2. So AX is equal to 6.131 meters per second square. Then for the last question, if AX is 9 meters per second square and AY 3 meters per second square, determine the maximum pressure that can develop in the tank and the point where it is occurring. So let's compute the slope. Tangent theta 3 equals AX over G plus AY, because AY is positive. So let's analyze first by computing theta 3. And let's compare the slope tangent theta 3 with the preceding slope if it is greater or lesser. So tangent theta 3 is 9.9 over 9.1 plus 3. So tangent theta 3 is equal to 0.7026. And this slope 0.7026 is greater than the preceding slope here, the red one, which is 0.75 over x, which is 1.2. 0.75 over 1.2 is only 0.625. So therefore, the slope should be greater than this second situation. So the surface should cross to the left of C and the top portion as shown in the figure, so that this is theta 3. So I'll call this distance x3, and this distance here, intersection with the top and D, as x2, and we form a right triangle here. So call that y3, the imaginary distance from A to this imaginary extension of the surface. So because this part is filled with water, and let's drop this distance, I call this x sub 4, where x sub 4 can be solved because tangent theta 3 is known. So tangent theta 3, which is 0.7026, equals 0.75 over x4. 0.75 over x sub 4. So x sub 4 is equal to 1.067 meters. Having found x4, we then express x3 in terms of x4, which is x3 in terms of x2. So x3 is x2 minus x4. So x3 is x2 minus x4, and x4 is 1.067. And then we equate the final volume of air here, because no liquid is spilled, to the original volume of air. But instead of volume in our experience here, we can reduce it to just area. So area of this trapezoid, final area of this trapezoid, represented by air here, because this portion will transfer here, is equal to the original area of air, which is 1.8 times 0.25. So area of trapezoid, 1/2 of quantity x sub 2 plus x3, where x3 is x2 minus 1.067 times height 0.75, equals original area of air 1.8 times 0.25. So we can now solve x sub 2, 1.8 times 0.25 times 2 over 0.75 plus 1.067, and the result is divided by 2. So x sub 2 is 1.1335 meters. Having found x sub 2, we can now compute y3, because this is also theta 3. So tangent of theta 3, which is 0.7226, is y3 over this distance. And this distance is 1.8 minus x2. So 0.7226 equals y3 over 1.8 minus 1.1335, which is x2. So y3 is 0.4683 meters. So the maximum pressure occurs at B, because B is the point that is farthest from the imaginary liquid surface. And since there is y component of acceleration, remember the principle, the maximum pressure is with y component of acceleration is static pressure at B times quantity 1 plus AY over G, because AY is positive. So static pressure, gamma of water, times HB times quantity 1 plus AY over G, where HB is the depth from imaginary liquid surface, depth of B from the imaginary liquid surface. So it is y3 plus 0.75. So 9.81 times quantity y3, 0.4683 plus 0.75 times quantity 1 plus 3 over 9.81. So finally, we can now compute the maximum pressure at B, equal to 15.61 kilopascals. So I hope you were able to understand the explanations and the solution to this problem.